49 minutes before midnight on September 8, 2023, a strong magnitude 6.8 earthquake struck a populated area of central western Morocco in what was the nation's largest earthquake in 268 years. This quake was heavily damaging and sadly quite deadly, with 4 reasons in particular. First, Morocco contains numerous structures composed out of traditional brick or, in more rural areas, mud bricks. Bricks are the absolute worst possible thing you can build with in regards to earthquake hazards. Only an MMI shaking intensity of 6 is needed to potentially cause a brick structure to collapse, yet this earthquake created a maximum intensity of MMI 7.5, which is equivalent to 31% the force of gravity. Thus, an area of 11,300 square kilometers, or a little less than an area the size of the nation of Montenegro, which in this case contained more than 150,000 people, may have seen numerous brick structures collapse. I might add that non-brick structures suffered generally less damage. Second, the earthquake occurred at fairly shallow depths of only 26.3 kilometers or 16.3 miles, causing significantly more damage than would have occurred otherwise if shaking had occurred at greater depths. Third, this quake occurred within an area of the country with largely 150 million to 650 million year old sedimentary rock units, including those in the high Atlas Mountains. Generally speaking, strong shaking from an earthquake propagates much further without losing as much energy in older rocks versus uniformly young rocks. And fourth, this earthquake occurred at what is considered to be the most deadly time for a quake to strike, aka at night when the maximum number of people are located inside various buildings. When combined, this resulted in more than 1,000 fatalities and a probable damage of at least $5 billion or 3.5% of Morocco's GDP. While this particular section of Morocco has, to the best of my knowledge, never produced a historical quake larger than a magnitude 5, the high Atlas Mountains to the south of Agafay contain a series of lengthy thrust faults. These are created due to compression related to the African tectonic plate moving towards the northeast, while the Eurasian tectonic plate moves towards the south. This magnitude 6.8 quake likely caused a 26-kilometer long section of the 124-kilometer long North Atlas Fault to rupture, which moved in a manner that contained both a horizontal and vertical component of motion to it. In other words, the earthquake which occurred represented the movement of an oblique fault where the hanging wall moved upwards in comparison to the footwall, but if you want to get more specific, it was technically an oblique left lateral reverse fault. In the vertical component, the hanging wall of the fault line moved upwards in comparison to the footwall. Yet, at the same time, from a top-down view, the right side block moved away from the viewer, representing its horizontal component. If you combine these two vectors, you get the exact motion of the earthquake which occurred. Although we do not know for sure the rate of such large magnitude earthquakes in the high Atlas Mountains, it could be as low as once every several thousand years, meaning what occurred was probably a highly unlikely event. In the next few days to weeks, more aftershocks or earthquakes triggered by the main shock are likely to occur with a 1/x frequency compared to the rate of aftershocks on day 1, with x representing the number of days which have passed since the main quake. Statistically speaking, the average largest aftershock is 1.2 magnitudes lower than the main quake, which in this case means there's a 50% chance of at least one magnitude 5.6 or larger quake occurring as an aftershock. There is also a low chance, probably around 6%, that at some point in the next 3 weeks, a quake larger than magnitude 6.8 could be triggered in the vicinity of the main quake. Yet, the odds that this won't happen are slightly greater than 94%. As a final note, I would like to thank this channel's patrons on Patreon and channel members on YouTube.